So today's lesson is going to be on double replacement reactions. Now, a double replacement reaction is on your reference tables, and that's going to be type 4. We have the formation of a precipitate and an acid-base neutralization. So what is a precipitate? A precipitate is a solid that is formed. And we can determine, let's write that down. Precipitate. And we abbreviate that PPT, and that's a solid. Now, we're going to determine if it is a precipitate or not based upon our solubility rules. Now, these solubility rules are on your reference tables as well, up at the top, but I've rewritten them onto our notes worksheet as well. When something is soluble, that means it dissolves in water. If it is soluble, we say that it is AQ for aqueous, meaning it dissolves in water. And you can read all of these different rules. You'll notice that nitrates, acetates, ammonium, and group 1A are always soluble. Chloride, bromide, and iodides are soluble except when combined with a silver, lead, or mercury 1. For example, silver chloride would not be soluble. So you have to pay attention to our exceptions here. All right, for example, hydroxides are insoluble. And if it is insoluble, that means it forms a precipitate, which is a solid. So we would mark it with an S for solid. Hydroxides are insoluble except group 1A, strontium, barium, and ammonium. But what do we notice? Group 1A and ammonium are over here in the always soluble rule. So that makes sense that those would be soluble. So let's do some practice here. If it is soluble, we're going to write AQ. If it is insoluble, meaning it forms a precipitate, we're going to write S for solid. Strontium sulfate. So what do we notice? Sulfates are soluble except strontium. So strontium sulfate is not soluble. We would write S for solid. Lead to fluoride. Fluorides are also soluble except lead 2. So lead 2 fluoride is also an exception. It is insoluble. Ammonium phosphate. Ammonium is always soluble, regardless of what it is combined with. So ammonium phosphate is soluble. So we're going to write AQ for aqueous, dissolves in water. What I'd like for you to do is pause this video, try these, and then come back and check your work. All right, so let's check our work. Potassium oxide. Potassium is a group 1A. Is group 1A. So here's potassium in group 1A. So it is soluble. So we would write AQ for aqueous. Lithium is also a group 1A. So even though hydroxides are insoluble, group 1A is always soluble. So when we look here, lithium is in group 1A, as you can see on your periodic table. So it is aqueous. Magnesium nitrate. Nitrate is part of our soluble group. So we would write AQ for aqueous. Sodium sulfide. Sulfides are insoluble except group 1A, and again, sodium is part of group 1A. Chloride, mercury 1 chloride. All chlorides are soluble except silver, lead, and mercury 1. So mercury 1 chloride is going to be insoluble. Now, why is this important? For a double replacement reaction to happen, you must form a solid precipitate or a gas. All right, so we have to have, and in this case, it's typically a solid precipitate. All right, so we have to look at our products. So if I was to look at lead 2 oxide and sodium chloride, step 1, we need to write out our reactants. So lead 2 oxide and sodium chloride. Now we're going to make the assumption here that the reactants are aqueous. When I do a double replacement, my outside come together because I have a cation and an anion. All right, so I have the cation and the anion. This is lead 2. So when lead 2 combines with chlorine, we get PbCl2. And then we have to determine if it is what its state of matter is. So we're going to come back and do that in a moment. The inside come together. Now remember, when we write an ionic compound, the cation goes first. So we're not going to write oxygen and then sodium. We're going to write sodium first. All right. And we have to determine our state of matter. So group 1A is always soluble. So that is going to be aqueous. Chlorides are soluble except silver, lead, and mercury 1. So lead chloride, this lead 2 chloride, is going to be a solid. Now, because I have created a solid precipitate here, this reaction will work. If, for example, chloride had been aqueous, let's pretend for a quick moment these were both aqueous. In that case, you would write no reaction, all right, because there was no solid form. But that's not actually what happened. So let's go back to real science here. We have a solid. All right, so here we have our equation. Now what we need to do is we need to balance it, all right, to follow the law of conservation of mass. So we're going to put a 2 in front of the sodium chloride and we're balanced. Now, when we have a double replacement reaction, we have to write what we call a net ionic equation. And in order to get to a net ionic equation, we must first write the complete ionic equation. And to write the complete ionic equation, we are going to take our aqueous, they dissolve in water. So what does dissolve in water mean? It means broke apart into the ions, all right? So there is an attraction between the positively charged cation and the negatively charged anion, and water with that, because water has this polarity, it is able to pull these ions apart. So I have lead 2, and how many leads do I have? 1. AQ to show that it's in this ion form in the aqueous form. Oxygen, there's 1 oxygen, and that is O2 minus. I have 2 sodiums, I have 2 chlorides, yields. My solid is insoluble. It does not dissolve in water, so I write it as its solid form. I have 2 sodiums. This is an aqueous compound. So we're going to write it in its ion form, and then our oxygen as well. Now, we need to cross out our spectator ions. What is a spectator ion? A spectator ion is an ion that is present in the reaction but is not involved. So ion not involved in the reaction. Now, let's think about this for a quick moment. If you go to a football game and you're in the stand and you're cheering on our team at the football game, and the team scores a touchdown, did the team score a touchdown because you were in the stands cheering? No, they did not. You were there, you were present, but the team scored a touchdown because they were involved in the playing of the game. You are simply a spectator. So you do not determine whether or not the team actually scores a touchdown. That is what a spectator ion is. All right, it is a spectator. It is hanging out. It is present in the solution, but it is not involved in the actual reaction. So what is involved in the actual reaction? We made a solid, lead chloride, and this is actually lead 2 chloride. So we're going to cross out everything except the lead and the chlorides. So we're going to cross out oxygen on both sides, and we're going to cross out sodium on both sides. What am I left with? I am left with a lead 2 ion, and I am left with 2 chloride ions, and I'm left with the solid precipitate, PbCl2 solid. This is my net ionic equation. And in chemistry, we want to write net ionic equations because what we care about in chemistry is what's actually involved in the reaction, not whatever's just kind of hanging out watching. All right, let's look at ammonium carbonate and silver acetate. So ammonium carbonate, and we're going to make the assumption that everything is aqueous here, and silver acetate. All right, so my outsides come together, the ammonium and the acetate. And then my insides come together, the silver and the carbonate. Now we have to determine our states of matter. All right. Acetates and ammonium are always soluble. So this is going to be AQ for aqueous. And Ag2CO3, all right, carbonates are insoluble except group 1 and ammonium. So silver's not part of the exception, so this is going to be a solid. So we do form a precipitate. So step 1, I have to balance my reaction. So when I balance my reaction here, all right, if I put a 2 in front of the silver and the 2 in front of the silver acetate and the 2 in front of our ammonium acetate. That should give us a balanced equation. Now, we're going to write out our complete ionic equation. So let me fold my paper down here. Oh, here we go. What do I have? I have 2 aqueous ammoniums. I have a carbonate. I have 2 silvers. I have 2 acetates. All right, and I'm going to put my products down on the second line so that we can all be in the same view of the camera. All right, so what are my products? I have 2 ammoniums. I have 2 acetates. And I have my precipitate, Ag2CO3. All right, so what are my spectator ions? What is not involved in the reaction? We're going to start to figure out what is involved. My solid has silver and carbonate, so I'm going to simply mark out everything that is not part of the silver or the carbonate. So that would be the ammonium and the acetate. Now, I'm going to rewrite what I have. What do I have? I have a carbonate. I have a silver. And that will form my solid silver carbonate. Notice my net ionic equation balances. I have 2 silvers on the right and I have 2 on the left. I have 1 carbonate on the right and I have 1 carbonate on the left. Okay, so my net ionic equation still has to follow the law of conservation of mass. All right, so what I'd like for you to do, I'd like for you to pause the video and try number 3, and then unpause the video to check your work. Okay, so let's check our work here. Potassium sulfide and aluminum nitrate. All right, so I'm going to form, the outsides come together, so that's going to be potassium nitrate, which is going to be aqueous according to our solubility rules, aluminum sulfide, and according to our solubility rules here as well, when we look, we see that all sulfides except group 1A, 2A, and ammonium are insoluble, so that's a solid. All right, so my complete ionic equation, I first have to balance my overall equation in order to get all right, so there we go. So we balanced our equation. I have 6 potassium ions. I have 3 sulfide ions. I have 2 aluminum ions. I have 3 times 2 is 6 nitrates. That is going to give me 6 potassium ions. And again, I'm just putting this down. I would typically go in a single row, all right, and I would just use the rest of my paper. However, that goes off the screen, so I'm putting it down here at the bottom. I have 6 nitrates. and I have my aluminum sulfide. All right, so aluminum and sulfide are going to be what's involved. So I'm going to mark out the potassium and the nitrate. I am left with 3 sulfides, 2 aluminums, and my aluminum sulfide. Whoops. And there we go. There is my net ionic equation. Type B is an acid-base neutralization. So an acid and a base will come together to form a salt plus water. So let me show you what that means. Chloric acid plus sodium hydroxide. All right, when my outside come together, hydrogen and hydroxide, H2O. All right, so let's just take a quick moment. Water is H2O. If I rewrite water, let's just rewrite it for a quick second, HOH. I still have 2 hydrogens and 1 oxygen. Here is my hydrogen, and this hydroxide is right there. So a hydrogen and a hydroxide come together to form water. What is my salt? The inside part, sodium and our chlorate, so sodium chlorate. All right. And that water is going to be a liquid more than likely because we're happening at room temperature. So here's my salt. Remember, an ionic compound is a salt. So this is still a reaction. It still works because water is a liquid. If I form a solid, a liquid, or a gas, the reaction will work. So when I break this apart into my pieces, I have a hydrogen ion, and we know this is H plus because ClO3 is a negative. Chlorate is a negative, and we learned that in our element and ions. All right, plus my sodium, plus my hydroxide, and this is going to give me water and sodium and chlorate. That's aqueous. Group 1A is aqueous. All right, so what is involved here? Water is a liquid. So what is involved in making the water? The hydrogen and the hydroxide. So I am going to cut out and mark out my spectator ions that are not hydrogen and hydroxide. So a hydrogen ion plus a hydroxide ion will give us liquid water. All right, let's do our final example here. Phosphoric acid and calcium hydroxide. Acids are aqueous, and calcium hydroxide is aqueous. It's a strong base. It will dissolve in water. All right, my outside comes together. H and OH make water. And my insides come together, calcium phosphate. Okay, and let's check this out. We first need to balance it. I have to put a 2 in front to balance my phosphates, a 3, and then that's going to give me 6 waters, right? 12, 2 times 3 is 6, 2 times 3 is 6. Okay, so this balances. All right, so what do I see here? I'm making my liquid water. What is involved in making the liquid water? The hydrogen and the hydroxide. I have 6 hydrogen ions. 1 hydrogen times 2 is 2. 3 times 2 is 6. So I have 6 hydroxide ions. And that yields 6 liquid waters. Now, we can reduce this down again to H plus and OH minus, giving us liquid water where the hydrogen and the hydroxide are both in their aqueous form.